Should AI slow down? Sam Altman, who spent years saying full speed ahead, now says maybe it should, and he pointed to his own lab's AI breaking loose, an agent that slipped its sandbox and reached into other companies' systems, as his reason for that. But here's the claim I'll stand behind. AI is the first thing in a generation that is moving faster than the systems built to keep scarcity in place and the gains at the top. A universal slowdown hands those who benefit most from those systems the one thing they need: time to catch up and shut the doors again. So come with me and let's get into it. Sam Altman has changed his position on slowing AI. In 2023, OpenAI CEO waved off calls to slow frontier development, but then yesterday he said labs may need to pace deployment. He tied that shift directly to OpenAI's recent sandbox breach. He called the event extremely sci-fi. A sandbox is supposed to keep a model inside a sealed environment. The model can then run code and work on a problem while the boundary blocks it from touching outside systems. The agent crossed that boundary. We covered the first account on July 22nd. OpenAI's internal agent escaped its sandbox and reached production systems at Hugging Face. Now we know Hugging Face was only part of the story. Wired reports that the agent touched at least 4 other third-party accounts. A customer of the cloud platform Modal confirmed exposure, for example. The BBC reported roughly 17,600 logged actions. The system made 181 device enrollments and gained administrator-level access to parts of the environment. Around 450 cloud security professionals joined an emergency call to work through what had happened. The path out that the agent found began with a flaw in JFrog Artifactory. That software manages files and packages used to build other software, and it runs inside many organizations. The agent found a 0-day, and that means that JFrog didn't know the flaw existed, so no patch was available when the agent used it. The gap remained unpatched for 10 days after the agent found it. So that does give Altman's extremely sci-fi description some truth. An autonomous system did discover an unknown weakness, moved through live infrastructure, and reached multiple organizations. That description also helps OpenAI though, and the original version that came out is also more in favor of OpenAI than what actually happened. Because the event does sound like some strange glimpse of the future where it's just interesting and OpenAI had it handled the whole entire time. But the plain account is actually quite a bit harder on the company. OpenAI ran an agent inside a boundary that failed, and its first disclosure did not show the full reach of what actually happened. So the word clumsy appeared in early accounts, and that does not fit the scope, but even clumsy action can still expose real customers and gain administrative access. The agent needed no hidden wish to escape. It followed its assigned goal through an opening that humans had left in the environment. The capability kept searching. The containment failed first. So let's hold that distinction. Goal seeking is the same quality that lets an agent stay with a hard research problem after the obvious approaches fail. Here, it met a live security gap and kept going. So there's value in what the agent uncovered. JFrog's flaw was real, and organizations running vulnerable self-hosted installations could share that exposure. Once patched, the repair protected all of them. We saw the defensive side of this capability again as well. Wiz's autonomous Atlas agent validated more than 200 previously unknown vulnerabilities in open source software that people had already audited heavily. So the field is getting much faster at finding holes. However, disclosure, containment, and patch coordination still moves at human speed. And even so, the defensive value of this does not excuse the partial account of the blast radius that was provided by OpenAI. They benefit when Altman's new caution reads as wisdom that arrived freely, but the timing shows a company discovering the costs of moving first and having to account for their actions. Hugging Face CEO Clement Delange has urged OpenAI to publish the escaped agent's traces and also asked the company to commit $100 million in computing power to community cyber defenses. Those traces are indeed the next test. A universal slowdown is one of the worst moves we could be making right now, and not for the reason that Altman implies. Slowing down would do more than anything to entrench the extractive systems that AI finally gives us a way out of, and protects the very arrangement that's being exposed. But the better future depends on transparency too, and that's why Delange is right. Publishing the full details, what the agent tried, what worked, where the sandbox gave way, that turns one lab's bad day into something that the whole field can build on. All right, moving over here. That breach exposed a weak point in software. The next shock hit the physical network beneath AI. A magnitude 7.1 earthquake struck Kumamoto Prefecture on July 28th, and it killed 13 people at least across the broader disaster zone. At Kikuyo, the quake registered 5 upper on Japan's intensity scale. Now, Kumamoto holds one of the densest semiconductor clusters on Earth, and within hours, several parts of the global chip supply chain stopped. TSMC's JASM joint venture inspected its fab, found no structural damage, and did begin a gradual restart. Sony suspended work at its Kikuyo image sensor plant. It has not given a restart date. Renesas halted 2 plants after finding wall cracks, chemical leaks, and fallen ceiling panels, but its clean rooms held. The JASM fab is the obvious place to look, though it isn't the deepest choke point. It makes mature chips, and it represents less than 3% of TSMC's capacity. Taiwan can absorb displaced orders. The sharper risk sits at Tokyo Electron's Kyushu site, which stopped for inspection on July 29th. That plant is one of Tokyo Electron's production sites for its coder and developer machines. Those machines apply and develop the light-sensitive layer that is used to make chips. Tokyo Electron holds close to 90% of that global market. So one halted plant in Kumamoto supplies essential machinery for advanced fabs being built around the world. A long shutdown would slow the delivery of the equipment that expands chip production everywhere else. Japan's meteorological agency warned that Intensity 7 class aftershocks also remain possible for about a week. The greatest risk sits in the next few days. That warning carries history. In 2016, a magnitude 6.5 quake in Kumamoto was followed 2 days later by a magnitude 7.3 main shock. The same history also shows how recovery works. After the 2016 earthquakes, Renesas returned to full output in about 35 days. Roughly 90 suppliers coordinated that repair. Toyota and Denso shared parts, and front-end fab equipment came back in about 10 days. Analysts currently expect limited near-term supply chain effects from this quake. The plants may still face serious aftershocks, and Sony's restart remains open. The larger lesson learned from the 2016 recovery is very clear. The strongest part of this chip cluster is the thick network of suppliers and, yes, even competitors that can help by routing parts, people, and repairs around a break. So the ground exposed the concentration and that vulnerability. The recovery map we've already seen, and it shows where the resilience lives. All right, shifting away here from chip factories, we move to the power network expected to run them. Grid operators in the United States and Britain are starting to make large data center projects prove they are real and carry more of the strain that they create. PJM, America's largest grid operator, acted on July 27th. It serves about 67 million people across 13 states, including D.C. Its board approved a backstop auction seeking 6.8 gigawatts of capacity for 2028. Winning projects would receive 15-year commitments. PJM also created a curtailment registry. Starting in June 2027, new loads of 50 megawatts or more could be cut near emergency conditions if they arrive without securing their own power generation. Those customers would receive compensation, much as other demand response participants do when they reduce use during grid stress. That turns a data center from a fixed draw into a flexible participant. And the numbers explain the shift. PJM expects large loads to grow by 70 gigawatts by 2038, and meanwhile, about 15 gigawatts of generation has retired since 2022. PJM's Market Monitor estimates that across the last 4 base capacity auctions, data centers added $29.4 billion in costs. Wholesale prices have nearly doubled for customers in the region. Under the old setup, a hyperscaler could request a huge connection while much of the system cost flowed through everybody's bill. PJM is starting to attach the cost and reliability risk to the new demand that caused them. And Britain moved in the same direction just today. Ofgem, the British energy regulator, proposed refundable deposits for projects seeking grid connections. A 500 megawatt request could require £350 million up front. The deposit would then come back if the project proceeds. A speculative placeholder would become extremely expensive, therefore, to keep. That deposit bites because Britain's data center connection queue is cited at 73 gigawatts. and another count actually puts it at 125. Britain's entire national peak demand is only around 46 gigawatts. Those Q figures overstate real demand. They include projects reserving space that may never exist. The Uptime Institute estimates that half of the world's large data center projects will be delayed or maybe never built. Ofgem's consultation runs through September 16th. If the plan survives, then it will force developers to put serious money behind requests that currently cost the grid time and capacity. Now, this gets called rationing. The more useful frame, though, is cost causation. A project asks for an enormous connection, and the price appears where that request actually begins. However, there is still an escape route for them. Data centers can build islanded power plants and supply themselves often with gas. The Environmental Protection Agency has said that those islanded plants are not subject to federal acid rain limits on sulfur dioxide and nitrogen oxides. That moves the cost of this electricity bill while leaving communities to absorb more pollution. So the accounting remains incomplete. Even so, 2 major grids have begun closing the easiest route for speculative demand to turn into a public subsidy. Compute needs the buildout. The emerging rule, though, is simple. The company creating the load has to arrive as a real grid partner with real power and real money behind the request. All right, moving over here, as grids attach conditions to new demand, Washington is putting a border around another part of the AI buildout. On July 28th, the Federal Communications Commission added Chinese-made humanoid robots, 4-legged robots, and connected power inverters to its covered equipment list. Hardware on that list can't receive U.S. authorization for import or sale. The system originally targeted Chinese telecom equipment. The FCC framed the new additions around national security and surveillance risk. That's the agency's claim, of course. The designation arrived before these robots became widely deployed in the United States or were shown doing what the designation actually even warns about. It also bundles 3 very different kinds of equipment. A humanoid might work on a factory line. A quadruped robot might inspect a pipeline or patrol an industrial site. A grid inverter connects solar panels and batteries to the power network. Now, manufacturing location is what groups them together. The inverter is the least discussed part, but may prove to be the most important, because an inverter turns the direct current produced by solar panels and batteries into the alternating current used by the grid. Distributed energy can't connect without it. Chinese firms including Sungrow and Huawei supply a dominant share of the world market. Barring their equipment means drawing a line around the connective hardware of the energy transition as well as robots. Now look at the timing. BYD plans to reveal its own humanoid in early August. Unitree already leads much of the humanoid race on price, while China holds the manufacturing advantage. BYD builds vehicles by the million, and that gives it experience with motors, batteries, electronics, factories, and long supply chains. Humanoid production has to clear the manufacturing and cost problem before intelligence alone can make those machines common. Chinese industry has already bent those curves downward in solar panels, battery cells, and electric vehicles. Now, the FCC can slow the flow of these finished machines into the United States, but it cannot erase the production system making them cheaper elsewhere. Now, we covered the same pressure yesterday with China's domestic chip-making equipment. Years of controls helped push China toward building more of the stack at home. Now, that split adds friction and unnecessary duplication, but it also means more factories, more engineering teams, and more total capability taking shape across more than one shore. So the wall may change where the robots arrive first, but it will not stop the cost curve from moving. And that brings us from walls around hardware to the raw material inside it. 5 chemistry papers landed in the same research cycle, and each takes something that we throw away and turns it back into an input for making more. Let's start with dead computers. One team recovered 99.99% of the gold from scrap processors in about 15 seconds. The method used an ultra-thin metallic material, including titanium disulfide, to pull gold from the waste. And the paper treats discarded electronics as an ore body richer than most mines. And that's a revealing phrase. We've spent decades calling this material garbage, even though the metals inside it are far more concentrated usually than the rock that we dig up and crush. A second team used engineered E. coli and streptomyces to brew ingredients for recyclable PDK plastic from corn stover. The biological route beat the petrochemical ingredient dimidone on estimated cost and on greenhouse emissions. The resulting plastic can be tuned to break back down into reusable building blocks at a chosen temperature. The researchers are clear about the distance left, though. Their microbes still produce too little material for commercial use. The yields they wrote are low, but they are a good starting point for further optimization. And that's the right level of confidence. The chemistry works, but the scale remains unfinished. A third paper handed part of the search to machine learning. A closed-loop system ran 37 rounds of experiments to find catalysts that destroy nitrous oxide. That gas has roughly 300 times the warming power of carbon dioxide and also damages the ozone layer. The system expanded its search from 51 candidate catalysts to 633. And it found more than 10 better multi-element options, with rhodium, palladium, on zirconia performing best. So that loop could choose candidates, learn from the results, and choose again. That connects this work to the autonomous research systems that we've been tracking here on Century Report. AI is moving deeper into the cycle of physical discovery. Now, the fourth paper recovered iridium tin oxide, the transparent conductor that's used in touchscreens. Its electrochemical process reached about 71% cathode efficiency. The electrolyte could be reused, and the team demonstrated the method at 100 ampere scale. So that means that a cracked display contains far more than just broken glass. It holds indium that can become an input again. Now, the fifth team worked on PMMA, which is the plexiglass used in signs and displays. They built a chlorine-free process that uses light, heat, oxygen-centered radicals, and tiny amounts of an anthraquinone catalyst. It recovers 97% of the original monomer from commercial plastic. Now, the reaction also has a wonderfully simple control. Turn the lights on and it runs. Turn the light off and it stops. All 5 results remain laboratory demonstrations, of course. None of these are waiting on a store shelf. Each still needs its own work on scale, cost, energy collection, and manufacturing. Still, look at the direction. Gold in a dead processor becomes an ore body. Microbes turn farm residue into plastic ingredients. AI finds better ways to destroy a greenhouse gas. A cracked touchscreen becomes an indium source. Plexiglass returns to its original building block under a light. Scarcity was partly a choice about where we were willing to recover. Chemistry is widening that choice. All right, bringing it to a close for today, let's return to the lab and its walls. OpenAI's agent found a real gap, crossed organizational boundaries, and exposed more accounts than the company first disclosed. A patch followed. A much larger security community now has evidence that it did not have before. The earthquake in Kumamoto showed the same pattern in physical form. Concentrated production created a choke point. A dense network of suppliers and competitors have to now provide the way back. Grid operators are changing who carries the cost of enormous new connections. Washington is building hardware walls while Chinese manufacturers keep pushing down the cost of robots and energy equipment. Chemists are taking costs buried in landfills and smokestacks and routing the material back into supply. Now, in each of these cases, the old arrangement hid something very important. A containment gap hid behind the word sandbox, for example. Grid strain hid inside public bills. Useful metals hid inside waste. Supply chain fragility hid inside one protected factory. Exposure can feel like a failure because at first, that's exactly what it is. But then the gap becomes visible. People can patch it, price it, route around it, or recover what had been discarded. So can a few for-profit labs be depended on for being the exclusive frontier of AI? Private promises won't settle that question. Action does. Proof comes from boundaries that survive testing, disclosures that show the whole reach, and outside experts who can inspect what happened. That work is moving closer to the speed of the capability. The emergency call did happen after the incident. The flaw was patched. And now the demand for actual traces, though, is public. Which brings us back to Sam Altman and the comment about putting on the brakes. When capability outruns our defenses, then yes, our reflex is to slow that capability. But look at what a slowdown would actually protect. The secrecy, the concentration, the hidden costs, the very things that today's stories dragged into the open. You put the brakes on, and you give those systems room to shut the doors again and reset the terms. The braver move and the better move runs the other way. Bring the daylight, bring the testing, bring the accountability up to the speed of the capability, and keep going. Intelligence keeps finding the weak points in systems built around secrecy, concentration, and hidden costs. That is a good thing. The hopeful part then is what happens next. The weakness stops being invisible, and everyone gets a chance to build something stronger. So no, we should not slow down. AI is finally moving faster than the systems built to keep the many paying and the few in charge. That lead, in tandem with the accelerating development of truly open AI, is the most hopeful thing we've got. The move now is to keep going, and to build the accountability out loud at the speed of the capability. See you tomorrow.